Now we're going to go ahead and take a look at example 2. And in this example, we're going to see an extension of an idea that was discussed again within a Calc 1 class as kind of an extension of the chain rule and derivatives. This is the concept here of related rates problems. Okay, you might recall these problems as being some of the scarier problems in Calc 1 classes where you had stuff, like a ladder is sliding down a wall. How quickly is the base of the ladder sliding out at the time when t is equal to, right? Like there were problems something like that. And sometimes those problems were a bit intimidating. Fortunately, I think here with the power of the chain rule, we're going to be able to go ahead and make these questions feel a little bit simpler overall. Let's take a look here at something like example 2 to see how this is done. The pressure P, the volume V, and the temperature T of a mole of an ideal gas are related by this formula here. Okay, if you're not familiar with any of these pieces of terminology or this formula, that's totally fine. You don't need to be aware of it. But just notice right now that what we have here is a formula that has two input variables. So this is like a Calc 3 multivariable function. Now what we want to do on this question is find the rate at which that pressure P is changing. So what we're seeing here is that in this question, we're interested in calculating the derivative of P with respect to T. This pressure might change over the course of time, and we want to calculate how quickly it's going to be changing. Notice here, though, that the variables of T, the temperature, and V, the volume, are also changing. In fact, the problem tells us at exactly what rates they're changing. It says the temperature is changing at 0.1 kelvins per second, and the volume is changing at a rate of 0.2 liters per second. So when I go ahead and I think about the function that I have here, I should recognize that T and V are functions that are dependent on time. The temperature changes over time, the volume changes over time. So when I go ahead and I calculate this derivative, I can set up what I just learned in the previous video about the chain rule. I can start by saying I need a partial derivative of P with respect to one of the variables. Let's start with T. Then, since T depends on time, since T changes over the course of time, I'm going to calculate the derivative of T with respect to lowercase t. So here, capital T is temperature, lowercase t is time. Now I'm going to add and take my partial derivative of P with respect to the other variable in there, which was V, and then take the derivative of V with respect to T. Now, as long as I can go ahead and evaluate each of these kind of four derivatives here, I'll be able to find the derivative that I was looking for. So let's quickly go ahead and try to fill in each of these values with what we've been given in the question. First off, the partial derivative of P with respect to T. This is super easy. Since V happens to be just a constant here, I can go ahead and state that my partial derivative is just going to be 8.31 over V. I can then say the derivative of T with respect to time is also going to be pretty simple. Note again, the question gave me that the temperature was changing at this specific rate. So I can go ahead and just plug in a specific number for that derivative. I can then go ahead and do my partial derivative over here. Notice that this would get me 8.31, oops, let me rewrite that, 8.31 T divided by V squared, and this would actually all go negative. Now, what I was doing there is I was just thinking about this as 8.31 T times V to the negative 1. And so I have to bring the negative 1 down, lower the power to negative 2, and then I can rewrite it in the denominator of the fraction. Okay, now I have to multiply on by the derivative of the volume with respect to time. So that is, how quickly is the volume changing? And we're told that value here is 0.2. So what you'll notice is what I've constructed here now is just a formula for what the derivative that I'm looking for is going to be. It still has variables in it, like V's and T's, and that's totally fine. Just like with every other derivative that we've pretty much ever calculated, variables are involved in it. However, if I want to evaluate this derivative at a specific moment, then I can go ahead and produce a final numerical value for the derivative that I want. So I can say here that when I have t equal to 300, which is what the problem tells me, and L equal to 100, we get that my derivative for the pressure is going to come out equal to 8.31. Oops, sorry, this should be V equals 100, not L. L was the units, not the actual label. But I should get then 8.31 over 100 times the 0.1 minus the 8.31 times my 300 over my 100 squared times 0.2. Now, of course, this is pretty messy, but if you had a calculator, you can go ahead and crunch this out. Like the question states, I'm going to go ahead and round my decimal here to the nearest thousandth. So if I do that, I think I end up with something like negative, let's see, negative 0.042. And the units on here should be units of pressure with respect to time, or units of pressure over time. Now, my units of pressure that I'm going to end up here with are kilopascals. Now, if you're not aware of that, that's totally fine. Notice that it was written here that that's what pressure is being measured in, and this is the way I would abbreviate that. And then, since this is over the course of time, I'm going to have this over seconds, since seconds is the units that's being used within the question. So hopefully this actually doesn't feel like it was that complicated of a question. One of the things that we need to just be aware of is that for some applications like this one, you would have to kind of be given a formula like you were given here, because there's no way I'm going to expect you to come up with this formula. But in other applications, maybe say something where you're computing the volume of something, or you're computing like a cost function for something, things where it might actually be easier for you to create the function of two variables that you need to start with. That might happen on worksheets or on homework assignments. So make sure that you are aware that you might need to do that and not be too surprised or intimidated that you have to come up with this function potentially on your own from time to time. Of course, if it's more of an obscure reference like the one that we have here, I will of course be providing you with that.